The second law of thermodynamics states that the entropy, or disorder, of a closed system is always increasing. So one way of thinking about entropy is a measure of disorder or chaos in the universe. So the more entropy we generate, the less energy is left over to do useful work. If you think about entropy statistically, you could think about it in terms of a puzzle, where you have to figure out how many combinations there are of putting 3 balls into 3 boxes. Well, there's 10. In 3 cases, you will have 3 balls in one of the boxes. There's one where there's a ball in every box, and the other 6 will have them all spread out to a different degree. That's straightforward enough, but when you scale it up, even by a factor of 10, things get much more complicated. Counting the permutations becomes impossible. Now if you imagine that there were trillions upon trillions of atoms and trillions upon trillions of boxes, then statistically you could see that it's much more likely that the atoms would be disordered rather than ordered. Perhaps the most significant conclusion from the second law of thermodynamics is the concept of the arrow of time, which tells you which direction time is traveling in. For example, if a process generates entropy, it will happen spontaneously and will be irreversible unless you input more energy. When I pour cream on my coffee, I wouldn't be surprised to see the 2 liquids mixing and becoming more disordered over time. I would, however, be surprised if the cream and coffee separated again after I had stirred them. An ice cube in coffee will melt and become a more disordered liquid, but under those conditions, it cannot spontaneously reform itself back into an ice cube. So you might be tempted to think that if this is true, and if entropy can never be decreased, then how can human beings or more complex living organisms even exist? Well, the key here is that humans are not a closed system. So we're always exchanging heat with our surroundings, and we're decreasing local entropy at the expense of the entropy of our environments. So if I take an egg and I drop it, then the second law says that this egg will never spontaneously unbreak itself. But even the initial laying of the egg doesn't violate the second law, because the hen took a lot of food and broke it down, so creating a lot of molecular disorder or entropy, in order to make this egg that I've just broken. So the second law states that a spontaneous process generates entropy and involves heat moving from a hotter body to a colder body. Now, a refrigerator doesn't violate the second law of thermodynamics because it's not a closed, isolated system. We're continually inputting energy in the form of electricity to try and keep the inside of the refrigerator cold, but at the expense of the surrounding environment. So if we turned off the electricity, then eventually the air inside the refrigerator would come into thermal equilibrium with the surrounding environment. So the concept of thermal equilibration leads to the idea of the universe's heat death. Now this is an idea where heat flowing from a hotter body to a colder body will eventually lead to a situation where all of the atoms in the universe are at thermal equilibrium, and there won't be any drivers for spontaneous processes, and things will just stop. But the good news is that this isn't going to happen for a very long time. So it's been predicted to happen in 10 to the power of 26 years. So that's 10 with 26 zeros behind it. So we can take comfort in the fact that we can continue to create things and draw local order from the chaos for a long time to come.